going over lab 2 projectile motion. So what is the purpose? The purpose of this lab is to analyze 2D motion of a low mass object and observe how non-negligible air resistance causes trajectory to deviate from ideal gravitational models. Procedure: we threw a loose ball of paper with a meter stick in the background and measured the maximum height of the ball. The model: we took our video after uploading it to Tracker. We received position versus time graphs, which we used to graph the experimental velocity and trajectory. We then used this information to create a glow script that would help us determine the drag force and the gravity force acting on our ball. Models and physics. We can use spreadsheets to compare our data and use Newton's second law of motion to determine if our data is accurate. So, setup. We applied Newton's second law, the momentum principle, to predict the motion of the ball. Because the ball's velocity changes over time, we know there's a non-zero net force that is acting upon our ball. This relationship is defined as acceleration equals net force divided by mass, where acceleration is directly proportional to the vector sum of all forces and inversely proportional to the ball's mass. In our computational model, we used the velocity update formula derived from Newton's second law, which is VF, velocity final, equals velocity initial, plus F net over m, acceleration, multiplied by our change in time. To accurately simulate the real-world trajectory, Fnet was calculated as a sum of constant force of gravity and the velocity-dependent drag force. Equations. For this experiment, we mainly used Newton's second law, which tells us about momentum, velocity, and position, as well as acceleration. The formulas we used are following. The momentum update formula, which is the change in momentum is equal to Fnet times the change in time. Velocity and position update, which tells us about how far the position of our ball changes. So x2 final position is equal to our initial position plus our velocity multiplied by our change in time. There is velocity, and then of course our drag force equation. So that is Ft is equal to the opposite of BV. So to determine our drag force constant, B, we used velocity at a given point and then plugged it into the equation mg minus bv squared. Experimental data. Here's the results when we took the data from Tracker and put it into Excel. Note the ball is exhibiting the expected behavior for both the vertical and horizontal motion. The origin was placed so the ball would approach the origin rather than going away from the origin or starting at the origin. And then here's our glow script model. So the computational model is demonstrating extremely similar behavior to our experimental model. Glow script versus velocity and trajectory. We had an issue with our velocity versus time, but otherwise we have pretty much everything that we think we should get. These are the code we use. So our data for our ball's initial position, we began at 0.832, 0.304, 0 meters. The ball's initial velocity is given as 1.576 and 3.6 meters a second, respectively, in the x hat and the y hat direction. Where we find the change in r is by taking our initial vector and subtracting it from our vector at t equals 0.03333. We can also determine our magnitude as being approximately 3.9 meters a second squared. Our experimental data aligns closely with the computational model, with minor deviations attributed to external forces. Horizontal motion, so the motion in the horizontal trajectory exhibits a nearly constant slope in the x versus time graph, including uniform motion. This confirms that in our initial no-drag model, the net force in the x direction was 0, F net equals 0, resulting in 0 horizontal acceleration. Vertical motion. In contrast, the vertical motion demonstrates constant acceleration due to the force of gravity. As the ball approaches its apex, the vertical velocity decreases until it momentarily reaches 0 at v of y is equal to 0, which is v of f, at y max, the highest height we get at the max, which is our apex. So after the apex, the ball accelerates downwards, confirming the presence of constant downward net force. Model comparisons. The slight variations between our experimental steady slope and the theoretical model suggest that while horizontal motion is nearly uniform, real-world drag likely causes a subtle non-zero decline declaration that the base model excluded. So sources of error. A primary source of error was parallel displacement and the manual tracking and tracker. Because the camera was fixed at an angle, the perceived position of the ball may have shifted slightly relative to the meter stick, leading to minor variations observed between our experimental data and the ideal computational model. Final questions. Terminal velocity occurs only when the upward force of air resistance increases to equal to the magnitude of the downwards gravitational force, resulting in a net force equaling 0. So the sum of net forces equals 0. At this point, acceleration ceases and the ball and the object maintains a constant velocity. In our experiment, the gravitational force remained the dominant component of the net force. Because the ball was thrown from a relatively low height, it did not have sufficient time to accelerate to the speed required for the drag force to counterbalance gravity, really. To experimentally determine terminal velocity, the ball would have needed to be dropped from a significantly greater height, allowing the velocity-dependent drag force to reach equilibrium with the weight of the ball. Minor deviations between our model and our data are likely due to computational rounding, manual point tracking errors, and non-uniform shapes in the crumpling ball, which creates a variable drag coefficient that our oversimplified model assumes is constant. And that's everything.